We conclude our tour of the chemistry of esters by considering reduction reactions with esters. So recall that aldehydes and ketones are reduced to primary and secondary alcohols respectively with sodium borohydride. You remember NaBH4 is the reagent that carries out those reductions. But you may also recall that NaBH4 does not reduce esters. However, this should strike you as being a little bit odd, because the carbonyl carbon in an ester is actually in a higher oxidation state than it is in an aldehyde or a ketone. In the ester, it's usually in the +3 oxidation state. Given that in chemistry in general, things in higher oxidation states are easier to reduce than molecules with an atom in a lower oxidation state, it should be theoretically at least possible to reduce esters. And it is not only just theoretically possible, it is practically possible to reduce esters, but you need a stronger reducing agent than sodium borohydride. And the reducing agent that we use is called lithium aluminum hydride. So the difference between sodium borohydride and lithium aluminum hydride is that you have lithium instead of sodium and aluminum instead of boron. Well, it turns out that one of these is really important and the other one is not important in terms of making it more reactive. Lithium aluminum hydride is more reactive than sodium borohydride because aluminum is more electropositive than boron is. So that means that the aluminum hydrogen bond is more polarized Al plus H minus, and therefore this reagent really does behave more like a source of H minus, much closer to free H minus than NaBH4 does. So incidentally, the reason why esters are less reactive or more stable, that's another way of fundamentally saying less reactive, than aldehydes and ketones is because the extra oxygen atom in an ester allows for an additional resonance structure for the starting ester. Okay, so you've seen in the context of all of these carbonyl groups that there is another minor resonance structure where you put the negative charge on the oxygen and the plus charge on the carbon, which is what is seen in the center here. But in the case of an ester, and then especially in the case of an amide, this minor resonance structure actually leads us to another resonance structure where we can put the positive charge onto the ester oxygen as opposed to the carbonyl oxygen, because this central structure can still be thought of as an oxocarbocation with an O minus coming off of it. Okay, so this is a little bit unusual. We have previously invoked resonance as something that stabilizes an intermediate in a reaction. Here we are invoking resonance to stabilize a starting material and make that starting material less reactive towards reduction and other carbonyl additions for that matter, even though it is in a higher oxidation state. So what happens when we treat esters with lithium aluminum hydride? Well, first of all, note that I wrote excess lithium aluminum hydride here. And second of all, note that I have written two separate steps above and below the arrow. First, we reacted with lithium aluminum hydride, and then once that reaction is finished, we can add water. This is an important difference from sodium borohydride, because with sodium borohydride, we have ethanol as a solvent that is present during the course of the entire reaction. Okay, so the product you get out of this reaction of an ester with lithium aluminum hydride is actually a primary alcohol. Okay, and then since this was a methyl ester that we started with, we also give off a molecule of methanol in the end after everything is neutralized. Okay, but the ester with the R group on it has been reduced to the primary alcohol. So the oxidation state on carbon then, on what was the carbonyl carbon, has changed from +3 to -1. Therefore, this is a 4-electron reduction. In other words, once you can get this thing reducing, it's actually going to reduce quite a bit. 2 hydrogen atoms are added to the carbonyl carbon as H minuses, and our mechanism must account for these facts. Similarly, the carbonyl oxygen is going to also pick up a hydrogen in the form of H+. Okay, so let's look at this mechanism. Okay, so the first thing that happens is we get nucleophilic attack of H-. Okay, I'm just going to draw this with one arrow from the aluminum hydrogen bond, and then we'll go ahead and put the minus charge onto the oxygen, just like every other acyl transfer mechanism that we've seen. Not going to worry about the aluminum any further. So after this step, H- has come in as a nucleophile, and we are at the tetrahedral intermediate that we have seen so many times. And what does the tetrahedral intermediate do? It wants to regenerate the carbonyl and kick off a leaving group. In this case, methoxide is kicked off as the leaving group. Okay, so these first 2 steps are the standard acyl transfer mechanism under basic conditions that you have seen in the last several videos. Except now, instead of producing a different carboxylic acid derivative, we have produced an aldehyde. Well, the aldehyde is more reactive towards lithium aluminum hydride and any other reducing agent than the ester is. So therefore, and this is an important point, the reaction does not stop at the aldehyde. Okay, so lithium aluminum hydride from this point onwards reduces aldehydes and ketones through the same mechanism as sodium borohydride does. So you get another molecule of H- adding to the carbonyl. You break the CO pi bond, put the electrons onto the oxygen, and then we are left with an alkoxide with the conjugate base of the primary alcohol that we're going to end up with in the end. Everything will stop here until all of the molecules have gotten to this point. And because an alkoxide, because OR- is a much weaker base than H-, this addition is irreversible, both the first and the second addition, and every molecule will make it to this point. We don't have to do anything to drive the reaction to this point. Now, to get a neutral product, once every molecule has gotten to this point, you add water. And when you add water, that protonates the alkoxide to make the primary alcohol product. Okay, it also protonates the OCH3- that you kicked off as a leaving group in step 2 to make a molecule of CH3OH. And you use, while water is strong enough to protonate this, we usually use water under slightly acidic conditions. You usually use dilute acid to do this protonation. It also decomposes all of the aluminum compounds into soluble aluminum, and they just go away and don't bother us anymore. Okay, so important point. You have to carry out the first part of the reaction in the absence of water, and the second part of the reaction we add water, and I'll get back to that in a second. I just want to put up a little graphic here showing the relative reactivity of the carbonyl groups with the hydride reagents. So aldehydes are more reactive than ketones, as we have seen over and over and over again. Aldehydes and ketones are reactive enough to be reduced by sodium borohydride. Then you get esters and, as we'll see in a minute, even carboxylate anions, which will not be reduced by sodium borohydride, but will be reduced by lithium aluminum hydride. And note that all 4 of these functional groups will get reduced by lithium aluminum hydride. You could, if you wanted to, reduce an aldehyde or ketone with lithium aluminum hydride. It's just the sodium borohydride is a much more practical reagent to use because it doesn't have the property that it may spontaneously catch fire. And lithium aluminum hydride may spontaneously catch fire. In fact, I have had it happen to me once. Okay, so a few more notes about this reaction that I want to come back to and state a little bit more clearly. So first of all, since you cannot use an alcohol as your solvent for this, the first part of this reaction, you must use an ether as your solvent. And the one that's normally used is diethyl ether, although you can also use tetrahydrofuran, which is the 5-membered ring cyclic ether. The reason why you can't use an alcohol or water as a solvent is because since lithium aluminum hydride is a much better source of H- than sodium borohydride is, and H- is a very strong base, the conjugate acid of H2, which has a pKa of 35, H- will react with any acidic hydrogens to get destroyed and just generate a molecule of H2. So that cannot happen. Therefore, we avoid water and alcohols during the reaction until everything gets through the first 3 steps, and then you add water, even acidic water, to protonate everything to make neutral compounds after the reaction is over. Okay, second of all, we need 2 hydrides for this reaction to take place, so we have to make sure we use an excess of lithium aluminum hydride. And then finally, it is possible, albeit difficult, to reduce carboxylic acids with lithium aluminum hydride. Okay, so you saw a hint to that in the graphic that I put on the last slide. But an even larger excess of lithium aluminum hydride is required, because what's going to happen is that the first equivalent that you add is going to act as a base and deprotonate the carboxylic acid to make the carboxylate anion. The carboxylate anion then gets attacked by hydride, and the result of this step is that you have an intermediate with 2 negative charges. Okay, this does happen. You can reduce carboxylates this way, but the reaction is not as smooth as the reduction of esters is. If we were to try to continue this mechanism a little further, we will encounter some difficulties, although we do know that this reaction takes place. Therefore, we're not going to consider the complete mechanism of this reaction. But just for the sake of being complete with our material, we do need to know that reduction of carboxylates is a possibility. The take-home message from this video is that lithium aluminum hydride will reduce esters. It will reduce them by 4 electrons all the way down to the primary alcohol, and that this reaction needs to be carried out in an aprotic solvent, namely ether, followed by an aqueous